Hello everyone, welcome to my channel Chemistry by ANR. This is Unit 5 of Class 12, which is the coordination compounds. There are two types of compounds. One is complex compound and the other is double salts. When we actually compare them, we generally compare them simultaneously. Like if I say double salt, an example of double salt, all of you, those who have done the practicals in your lab classes, you might have noticed a salt which is named as Morse salt. Okay, so Morse salt is a salt which is a double salt because in its formula, Morse salt in its formula, it has two simple salts combined in a fixed ratio, that is FeSO4, ferrous sulfate, NH4 whole twice SO4 ammonium sulfate dot 6H2O, which is known as ferrous sulfate ammonium sulfate hexahydrate. Now, this type of salt in its aqueous solution will furnish all the ions that it has, like ferrous ion Fe2 plus in its aqueous form. Then sulfate, you will get SO4 2 minus from here and here, ferrous sulfate and ammonium sulfate. So 2 moles of it you will get. You will get NH4 plus, and of course aqueous solution, so H plus OH minus simultaneously. And you must keep in mind one thing, that since double salt has all these ions, you actually can test the presence of these ions in it. Like if you want to test the presence of sulfate, you can use the barium chloride test, you can use lead acetate test. If you use barium chloride, then you will get a white PPT that corresponds to barium sulfate, BaSO4. Now, if you want to test of NH4 plus, then you can use Nessler's reagent, which is K2HgI4 in presence of NaOH. NaOH and Nessler you can use, and you can get a brown PPT. So these are corresponding to your practical experience in your lab classes. But the fact which I want to emphasize over here is, in double salt, the constituent ions can be tested by chemical method. Now, complex salt doesn't contain all ionizable part. Suppose I say K4FeCN whole 6. This is potassium ferrocyanide. Now, in its aqueous solution, it has one ionizable part and the other non-ionizable part. So, if this ionizes, you will get 4K plus and you will get FeCN whole 6 4 minus. 4 minus. So this is what is the counter ion. This is your counter ion. And this non-ionizable part is known as coordination sphere, or it is known as coordination entity. In this coordination entity, you have a central metal atom or ion, and you have surrounding atoms or groups of atoms which are known as ligands. Ligands are atoms or groups of atoms which is covalently bonded, coordinately bonded to the central metal atom or ion. So that is known as ligand. So we will come to these parts in the next module again. But the part which we are going to emphasize is about Alfred Werner, who was a Swiss chemist and who has conducted an experiment, simple experimental technique by which he has explained what is called a primary valence and what is called a secondary valence. Like in a series of compounds like cobalt 3 chloride with ammonia, if I say cobalt 3 chloride, then obviously I mean COCl3 along with ammonia. So in different proportions we can see that he has taken, and in different proportions of ammonia the color of the solution differs. Now, he tried to precipitate out the Cl minus using silver nitrate solution, excess of silver nitrate solution, to actually test the presence of Cl minus ion. And he has seen that In this case, the first example, 3 mole of AgCl is getting precipitated. That means there are 3 ionizable Cl minus ion. In the next case, it is 2 moles of AgCl which is precipitated, and you have been supplied with 3 moles of Cl minus, out of which 2 moles are getting precipitated and 1 Cl minus remains unionized. So the next one, again, 1 mole of AgCl is precipitated. That means out of 3 moles, 2 moles are remaining unionized. Now, the Cl minus or the negative ion that is actually causing the precipitation of AgCl is named as the primary valency, the ionizable part, the counter ion that has been obtained. Here, the negative ion that has been obtained is the primary valency. And the secondary valency goes for the groups or the atom that is directly bonded to the metal ion using a coordinate bond. So let us see that in the coordination compound, these are the main postulates as given by Alfred Werner in 1898. In coordination compounds, metals show 2 types of linkages. Just now we have seen these linkages can be known as 2 types of valences, primary and secondary. The primary valence is the counter ion, the ionizable part, which is satisfied by the negative ions. And the secondary valencies are the non-ionizable part, which is actually satisfied by the neutral molecules or negative ions. The secondary valency is equal to the coordination number. Coordination number actually means how many coordinate bonds. It means number of coordinate bond formed by ligands with the metal atom or ion, formed by ligands with metal atom or ion, that is known as coordination number. Now please keep in mind that all the ligands may not form single bond or double bond only. So the number of coordinate bond a ligand can form with the central metal atom or ion is known as its denticity. That means how many coordinate bond it can form. So I can say the coordination number is actually equal to the summation of number of ligand into its denticity. Suppose I say oxalate ion is actually named as oxalato, C2O4 minus. Now this has 2 donor sites, C double bonded O, this is O minus, and a C double bonded O, this is O minus. So there are 2 donor sites, and so it has a denticity 2. So if I say this oxalate is present near the central metal atom or ion 2 in number, that means what is its coordination number? 2 into 2 it will be, because 2 is the denticity. So regarding this, again in the next module we will elaborate. So let us continue with this. Now, the atoms or groups, how they are aligned in space, the spatial arrangement, corresponds to the coordination polyhedra. Now, we should always remember another fact with respect to the coordination polyhedra, that if the coordination number is 6, then your coordination polyhedra or structure will be octahedral. And in an octahedral structure, you have central metal atom and there are 6 ligands like this attached. So if I say the ligands are all coordinate bonded, it's like this, coordinate bonded to the central metal atom. So this is your octahedral structure. This is the coordination polyhedra of a coordination number 6. If the coordination number is 5, it can be first a TBP structure. So I can say this is the TBP structure of the metal and the ligand, the way it is aligned, or it can be a square pyramid. So I'll say square pyramidal structure. So if it is a square pyramidal structure, then these are the 4 bonds and this is your 5th bond, square pyramid. If it is coordination number 4, and then we'll get a tetrahedral form. Always remember tetrahedral form to write it in a proper spatial arrangement. This is the tetrahedral form. Other than tetrahedral form, it can be square planar as well. So this is your square planar form for all the coordination polyhedra. We are seeing coordination number 6, 5 and 4. So next over here, there is an example question, say of 5.1, which is very important, and you are supposed to tell and assign the secondary valences. And what information is given over here? How many moles of AgCl is precipitated per mole of the compound? That is being given. So it has 2 Cl over here and 2 mole is precipitated. Obviously, there is no more Cl remaining inside the coordination sphere. The coordination sphere has only 4 NH3, and NH3 is monodentate ligand. It has only one donor atom, that is nitrogen, and so the secondary valency is 4, corresponding to 4 NH3. In the second case, we are seeing again there is 2 moles of AgCl precipitated. There are 2 Cl. Obviously, the 6H2O is the coordination number it gives, and so the secondary valence is 6. In the next example, HCl is neutral ligand, so HCl and Cl4, but none of them are precipitated. So the coordination number should contain 4 plus 2 equal to 6 secondary valence. And then in the next one, there are 3 Cl, 1 is precipitated as AgCl, 2 remaining, plus 4 for NH3, secondary valence equal to 6. So this is how you are going to see secondary valence and primary valence, the counter ion which is ionizable. Difference between double salt and complex salt in the first part of the module I have told you. Here we can see carnallite. This is the formula of carnallite. More salt. This is the formula of more salt. Potash alum. These are the common double salts, and this part is equally important for your practical viva. So do study this part. I hope if you can recall what is a primary valence, what is a secondary valence, if you can find secondary valence, if you can distinguish between double salt and complex salt, if you know the postulates of Alfred Werner's theory, then you are done with this module.